interactive session. It was actually the brainchild of Professor Obade. We have been thinking of how to resuscitate this opportunity of staff seminars. But when Dr. Adeyemo heard about it, he grabbed it and expanded it to the whole members of staff. And I bought into that idea. So I want to welcome us. It's an opportunity for us to interact and also to learn from one another, and also to tap from the knowledge of those that are existing before us, especially our living ancestor, the GOS, the category, is here. And whenever I call him, I'm proud to say that. Even if it is 1 minute interval, he will always answer. So I want to appreciate you, sir, for this opportunity that you are giving to us. To the students, I think this is also an opportunity. I don't think we had this opportunity as students, because when we came in, some old people had gone and things were going like that. But to the students, I think this is an opportunity for you to learn and then to chart a course of picking it out. Whatever anybody talks about today, you can pick one or two and then mix it up with your field and see what can come out of it. That is the hybrid that is going on now. Every area of mathematics is in our own. And so don't say, I'm in this area, therefore this one is not good. Or I mean, that is the essence of our language. To see where from one or two you can start to come into your area, and then we can collaborate and make progress. So I wish us nice experience today and say you're welcome. Thank you.
Yes. So let me get the program. The presentation from the university. So 10 minutes, 5 minute presentation. Some will use like some will just summarize it. The whole idea is to, just to be familiarized with the idea of our research. So I'm calling on Dr. Deko first.
Well, first to my distinguished emeritus professor, who is my godfather and my grandfather in this research field, I welcome you. And also to my teachers, Professor Obade taught me in London. This is one on side. Yeah, we're in the same sense. Yeah, taught us there. So I'm happy you are here. Then our privilege to be taught by Professor Yewade when I needed some tools in physics. So I had to go for like a semester course. And he was asking me, because you really want to know this aspect. How was this question? I said, I don't know yet. Let me just sit in your class. Yeah, so I learned about composite theory and I think which other course was that? Yes, particle physics. Yes, thank you very much for that. Feynman diagram, something like that. So then Professor University was also my teacher here, and Professor from London level the professor. So I'm glad to have to give this talk. To my other colleagues and students, I'm happy to also give a talk for us. Tell us some of the things that some of us have been doing, particularly me in this case. Yeah. So I'm sorry I didn't present this slide because I've been wondering on how to go, and it seems to be so wide for me, but I just tried to scribble some things down. Maybe I'm going to read some parts and I'm going to cover some parts. The first thing is this. Well, I did my PhD, MSc, and PhD here, and thank God for all my mentors. And my area of research is actually stochastic analysis and its application, particularly in functional stochastic differential equations and equations. Although I also do some other things that are closely related to it and some other aspects of mathematics. For example, when I supervise students, I supervise in the area of modeling, numerical analysis, functional mathematics, quantum computation, then some aspects of mathematical physics. That's to mention some of them. So in any case, I work in almost all fields, particularly at the grassroots level. But for my research, lower level, we talk about art, about art, and all those things. Then we now focus on them. Generate tools that basically are employed in establishing results. These tools can be sometimes complex as such that we might need to put what we call theorems, lemmas, and all those on them, and that becomes established results. Therefore, how do we employ this in the advanced level? For my own area of research, physics is in the foundation. I didn't understand this for a long time until when I had to seriously look at key things in my work. The first problem I had was, what is the meaning of annihilation and creation? That was what originated my going to physics. What is quantum field theory? I was not taught, and these are the structures that are embedded and form the basis of what I need to use in research. And therefore, I ventured into that, and I discovered that there is no way I can do this except if I learn more on operator algebra. And mind you, operator algebra is a more advanced method that extends more than analysis. And in operator algebra, you have so many aspects. Generally, you start with a star algebra. I think this is more general. Then you maybe extend to the level of star algebra that you this is an evolution on an algebra. So you have the sister algebra, and presently what we use here is the partial star algebra, which is more general partial star algebra as introduced by U.S. Chicago. Since I have to learn more of this, I didn't have a choice. I have to study some of these works. I have to go back to the root. There are some papers I didn't get online. I have to go to him, and I prayed and I requested from him that use some of these papers. Can be put in the library for us, because when you go online, you are never be able to get them free. And thank God he's here with us. And there is no place that I have presented the work, and they will not ask me, why are you dealing with this much rigorous tools in mathematics? The other second question they asked me is, what is the application of this? And you see, I've also avoided that, Prof, what is the application of what we are doing? Maybe today, or maybe during the conference, I'm going to learn more about it. Therefore, our quantum stochastic differential equations that we work on actually extends what we know as the quantum stochastic differential equations. Now, the way it follows, there are different classes. The class we use, basically, is the Austin-Partisality formulation. In the Austin-Partisality formulation, it is the simplest form of PSD that actually extends the Ito calculus. The Ito calculus we know is extended from use of random variables, introducing what we call the noise, and it gave us what we call the Ito calculus now, where we have the Ito SDE, SDI, and all this stuff. But here, in the HP case, we have the introduction of operator value variables, or let me say general forms, that has the annihilation, the creation, and sometimes people call the number operator. Let me just use N. Okay, this combination forms the noise, okay, by matter of use of tools from tensor algebra, where we use tensor product, to generate them, or what we call a Fock space. Okay, the Fock space is generally a Hilbert space, but coupled like an infinite dimensional Hilbert space. Whatever it is. So this is how the basis for quantum stochastic differential equation is formulated. Now, not to bore you too much, where we start from is generally the canonical commutation relation from physics and the canonical anti-commutation relation. Okay, from there, all this is generalized and brought up. Then is how do we now use some of these things? For my study, I have tried as much, and I'm still working on them, to see how we have the applications. The applications exist already in the field of quantum stochastic equations, in the field of optics, or open systems, for quantum information or communication, like quantum cryptography and quantum computation. Recently, I started work on quantum computation. I mean, he can bear witness. He was here last year when we organized an IBM quantum for students. He gave a talk, I gave a talk, and one of our other lecturer from chemistry also gave a talk, looking at the quantum use from different perspectives in physics, in mathematics, and in chemistry. We gave it on this floor. And this was supported by some of the students and by IBM. Recently that I have started working on quantum computing, I have seen that there are a number of tools which are embedded in what our functionality stands for. For example, you have unitary operators. The objects in quantum computation are unitary operators. And this is embedded in physics. Therefore, there is no way anyone can run away from it. Okay, so the last time I gave a talk here, I was able to show these connections. But because of the time, I cannot take all the time. This is the idea behind a number of the things I do, starting from what we know as classical related to the quantum. Recently, I also have one of the senior authors in mathematical physics, Professor Kadi, that I'm also collaborating with. He is also, showing the use of some of the tools that are embedded in our analysis here that we use in mathematical physics. So, a number of things, as I said, there is too much of things to talk about, but cannot be simplified in 10 minutes. So I'm so sorry that I cannot go further than this because I've been told that the time is over. But this is the basic of what my own kind of research is. I hope if I've been able to explain something. So if you have questions, maybe. Thank you very much. So if there are questions from anyone?
Did you find any applications?
Yes, for now, I've not still been able to do the applications. The nearest one I can see clearly is the one that relates to quantum computation. But because that one requires a more simplified mathematics. The substance of mathematics here is much more higher. You need to do rigorous work to understand about 5 areas of core mathematics. Operator algebra, quantum physics, differential equations, differential inclusions, about 3 other areas. So that means if somebody has to work in this field, he has to be patient. Because if, for example, I have to introduce you to what you have to do here, I will give you materials to read. I won't stress you. Those students that have worked with me at Master, they know. I will tell you, don't mind, you won't spend too much money, but when you need to spend, I will tell you, go and read this material, come and pass it to me. So by the time you are passing it to me, a lot of things you don't understand, I get to communicate with you. For example, some of my students have seen somebody who has worked in the area of quantum control, then quantum control in 2 ways. Either the white noise, then we have the focus case, whereby they use the classical control instead of the quantum case. Yeah, and the quantum finance. So all these have physics in their basis. For example, you use the energy operator, which is Hamiltonian, and you split and work with them. So a lot of these things are there that we are doing presently in the department. So these applications can come. First, in PSDI we have it, it's shown, we're trying to work on and extend it. But in QSDI, which is quantum differential equations, I can bet it with you, nobody has done the application. So we want people to come and work. I'm sorry, okay, it's not very but the application in the context of seeing most of this simplified physical realization. Yeah, because for some of us, we have, I and Professor Budiero, we have discussed it so many times, that the only way it could be easy for us is when we bring some of these QP people here, because they still not want to do what we are doing. In fact, this is one of the initiatives behind this conference, that we want to bring them to ensure that they should come here and see that we are doing it even better than what they are doing. But they do not want to recognize it us. The only ones they don't want to follow us. So we are surely going to make them see that what we are doing is better. So that is where my key point is. But when it comes to numerical application, Ayola has done so much. Yeah, that you can see. But they still want to run away from it. So that's what I mean, sir. Thank you, sir. Okay, sir.
I just want to, from what you said about the applications, I'm just thinking when one relates relativistic quantum mechanics to non-relativistic quantum mechanics in terms of these operators, the algebraic creation and annihilation operators. The creation and annihilation operators are actually extensions of the ladder operators in non-relativistic quantum mechanics. So these ladder operators are used to actually traverse the spectrum of the system. So in that way, we already know that the system has certain allowed energy levels, and use the ladder operators to actually go through, to travel through, and in so doing, you are able to extract what are the quantitative values of these energies. Now, when you now come to relativistic quantum mechanics, the number of particles in the system change. In the non-relativistic, the number of particles is fixed. That's why more or less, those operators are just ladder operators. You are just traveling through and then obtaining quantitative values. Now, in the case of non-relativistic now, since the number of particles can change, that means you can have energies being created. So in this sense now, if you now consider this in reality, that is in nature you have the natural oscillator, where high energy particles are colliding. And as they are colliding, you cannot predict what kind of collisions will occur, what kind of creation will occur, what kind of annihilation. So there is a stochastic element to it. So I'm thinking, maybe if you want to look at this natural accelerator or natural collider, that's in the cosmos, okay, that may be a strong area of application of this.
Thank you so much, very much, Paul. Yes, I actually appreciate this because, you know, a lot of times when I interact with physicists, I tell them, I don't know physics, so because when it comes to the core of these descriptions, I have to learn it, and I know. Particularly, if you have described it now, it gives me the kind of picture that guarantees that our KSDI can operate in that setting. Because the stochastic element, the observability is high. I mean, and with what you have just explained now, it gives me cause to need to learn more in that field.
So I think we are doing fine from our discussions.
Yeah.
But just that you might want to look at this area as an application area, because that borders on cosmology.
Okay.
So people are really trying to understand such cosmological phenomena. So you might want to just look in that area. I think the mathematics is, you have it, which you are building, yes, just the application area.
Thank you,
that's why I'm saying.
All right, thank you, sir. Okay, sorry.
Yeah, I had mentioned something about
number operator, yes.
I need to understand that this number operator can be used in calculating different states. And when this is coming from square integral representation of certain semi-analytic have what the mathematicians now wavelengths. So it is used in handling wavelengths.
Thank you very much, sir. Because the number operator is also called the gauge operator. Yeah, so I've also noted that, and I've also
just an extension of the Poisson process.
Yes.
That's the gauge operator or the number operator. It's the extension of the Poisson process. Poisson process counts. And so this one is supposed to be a replica or an extension of the Poisson process on an infinite dimensional universe space. So it becomes unbounded. It's an unbounded operator. And so you can work with such. But applications of these are everywhere. For example, if you look at your quantum-stochastic differential equation, if you want to discuss quantum-stochastic differential equation with control, then you need inclusions. You can't discuss them robustly without talking about inclusions. And there are many quantum-stochastic differential equations with discontinuous coefficients. How do you discuss those? You need inclusions. So there are many areas where these things appear. That is discontinuous quantum-stochastic differential
differential equations, they are here. So how do you discuss them? So you need inclusions. So you apply inclusions there. So it's not a question of there's no place to apply it as. And also in control theory, control quantum stochastic differential equations, you also need inclusions. So with that, and then you can go into looking at open and closed systems, and this is coming too. Open and closed quantum systems. They come in discussing them. That's the thing. So we have all that. There are many areas of applications. So if we actually focus on them, but each area of application requires more and more mathematics. You need to delve into issues of control and all that, because you need a different space for control variables. So have a space of control variables, and which you tweak in order to have your quantum stochastic control equations. If when you tweak those things, you have the control which controls the system. So you need inclusions in order to do that.
Thank you very much.
Your family, I mean, you mentioned that you've been thinking about quantum computers and quantum computation.
Yes.
So one practical problem in quantum computers is decoherence
Yes.
and also error correction. Maybe this might be now have a more powerful way or better protocols
Yeah.
for this mathematical thing.
That's what I said before. You need this for open quantum systems, which you actually need in quantum computing, decoherence, error, and all those things. So you need this thing. So it's already there.
Thank you, Prof, for all the comments. I've noted it, and I will ensure that I push my research also into that area. Thank you, sir.